Hello, my name is Kenneth Chang, and today I'll be presenting Lab 5 Magnetic Molasses. So for the purpose of this lab was to explore the principles of Faraday's law and the electromagnetic induction by observing and modeling the motion of a bar magnet falling through a conductive aluminum tube. Also investigate the relationship between the magnetic field, induced current, and forces acting on the system, and create a computational model. Our main results for this lab was the experimental time was 1.252 seconds, and the computational model was 1.632 seconds. So the fundamental physics principles used in this lab was Faraday's law, Lenz's law, Biot-Savart law, and Newton's second law. So Faraday's law is EMF is equal to the time derivative of magnetic flux, and Lenz's law adds this negative sign, which is for the induced current, which is the opposing force. Um, and using Biot-Savart law, we can derive these two formulas right here, which give us magnetic force. So some possible error in this lab is the magnet hitting the sides of the tube, time measurement inaccuracy, and air resistance. So some assumptions we made were negligible air resistance, uniform conductivity throughout the aluminum tube, and we assumed that the magnet was ideal magnetic dipole. So in the experiment, the system was the bar magnet and the aluminum tube. The surroundings was everything else and gravitational force. And the initial conditions was that the north pole of the bar magnet was facing downwards, and the bar magnet started at the top of the tube, and the initial velocity of the bar magnet was 0. So for the procedure, we first set up the aluminum tube vertically and position the bar magnet above the top opening. We then release the magnet into the tube and capture its motion until it exits the bottom. We then review the video to find the entry and exit times of the magnet. We then calculate the time it takes to pass through the tube, and we repeat this experiment 5 times. So for our experimental values, we got an average time of 1.252 seconds, and this is a recording of one of our trials. So as you can see, we are recording a stopwatch too. So we see when it exits, and we see when it enters, and we see when it exits, and we do exit time minus entry time. So for our computational model, we first set up the dimensions of the tube, and we also set up the properties of the bar magnet, and we got a magnetic dipole moment 3.2 from lab 3. We also initialize our initial conditions. We created a function that calculates the magnetic field of the bar magnet, and then we also created another function that calculates the time derivative of the magnetic flux through the tube or on each ring of the tube. And then we then calculate the total magnetic force, which is the magnetic force of on the magnet and the magnetic force on the ring. We then sum up the forces, adding magnetic force and gravitational force. We then create functions of the bar velocity and position using Newton's second law. So for our computation, this is what is produced when we run our program. So the red color represents a counterclockwise current flow, and blue represents a clockwise current flow. And we found this by using right-hand rule. So what would happen when you flip the magnet around? We would observe the exact same results, just the colors would be flipped. So the computational model estimation is 0.38 seconds greater than our experimental value. The computational model doesn't take into consideration miscellaneous factors such as air resistance or the magnet hitting the sides of the tube as it falls down. So this is our velocity versus time graph, and we can see that when it first enters, it accelerates when falling down through the tube, but then the magnetic force of the induced current counteracts the force of gravity, and right here we have our net force equal to 0 since our velocity is constant, and then once it exits the tube, it starts to accelerate again. So for our discussion questions, for the first discussion question, it would dramatically increase the braking or induced magnetic force because by Ohm's law, the induced current value would be much greater. This means that the bar magnet will fall much slower. And for the second discussion question, this will cause a disruption in the flow of current and less loops of current, which would weaken the braking force, and the bar magnet will fall much faster.